I work at ACNR. I'm a kind of a systems developer focusing on like pretty low level security stuff. And I've been there for about 8 months now, I think. So not super long time, but yeah.
And what are you going to talk about today?
Today we'll discuss the value which emulator-based snapshot fuzzing could bring to you as a security tester as a part of your tool suite. So we'll go through like the benefits and like when emulators could be used, what they're good for.
Don't spoil everything.
We'll also discuss like when you should build your own emulator and when to use like a proper actual stock downloadable one, but it's usually best to build your own. So yeah, we'll discuss how to build it too.
Fun.
Yeah. All right. Yeah, so this is like my favorite topic. So this is great to be able to talk about. I don't have any fancy PowerPoint, but I have this editor here. So I've just written like a markdown file, and we'll browse through this quite slowly. We'll structure this talk so that we start in a very basic manner, breaking down like the terminology for people who are not super used to this level of security work. And then we'll go through like the use cases for this kind of stuff. And in the end, if we have time, we can look at like a proper demonstration too. So let's get going. So I don't have any screen mirroring here, but I have the same document set up on another page, but this will be just fine. Okay, so does anyone here know what fuzzing is? One. Good, great. So for those who didn't raise their hand, it's basically a form of robustness testing where you identify a certain point in a target program which processes data in any way. And you want to attack this point of the program. So the way you can do this is you take valid inputs and you make them fuzzy. That's the fuzzy testing. And you make them like corrupted and you throw them to the processing part of the program to see if it breaks or if it handles the mutated inputs correctly or if it crashes. Your goal is usually to try to find a bug, right? So, and to be able to do this, you have to be able to run the program, right? You cannot just look at it and try to make it like process your data. You need to actually be able to step through the instructions somehow. And if the target is not built for your host architecture, you'll not be able to run it on your host processor, right? And that's when you need an emulator. Yeah, so that ties these two things together, right? So now let's talk about what an emulator is. There's a lot of different definitions, but my definition, and ours tonight, is a software system that emulates a hardware system. The main hardware systems we're interested in are the CPU and the MMU. So the CPU is the processor, and the MMU is the memory management unit. So it's the thing that translates virtual addresses to physical addresses and finds them in physical RAM, right? So usually programs interact very little with like devices other than the CPU and the memory. like if you compare the ratio of CPU versus like device usage in a program, it's like, yeah, it's only CPU, right? Therefore, we don't really care about anything else than memory and CPU. So right now, our emulator defined here tonight, it's CPU and memory software which emulates hardware, right? If you work as a security tester and you perform security assessments of programs, you will encounter some difficulties somehow. You might have a program which you don't have access to the source code. And if you don't have access to the source code, it could be quite tricky to figure out what it's actually doing. Program could be obfuscated in such a way that it's very hard to figure out the actual functionality of the program. Or it could be built with like a programming language that makes it very tricky to reverse engineer. Could be basically, to be able to run it could help you a lot in like understanding the functionality. There are also programs which have like a extremely long startup time. If you think about like a Microsoft program, like Excel, or maybe an operating system, or stuff could take like several seconds or even minutes to start. And if you're trying to fuzz this program, you really don't want to like run through this startup time once every fuzz case. If you do that, like the number of clock cycles spent actually fuzzing the program compared to setting up the program state is like 99 to 1, right? So you really want to bypass that issue. And there could also be like, if you imagine a very complex and a big system, it could require a lot of state to reach like any interesting point. If you think about like a base station with a cell phone connection, and you want to test the base station somehow, you might require like 50 sequential session packets being sent back and forth before you even have like a proper connection which you could start fuzz, right? And if you're going to do that every fuzz case, you won't be able to fuzz anything. So we want to bypass that. And another issue that could occur is that you might find a crash, but the program you tested were in such a state that you will never be able to reproduce it deterministically. Say, for example, if you manage to crash this base station which you're testing, like you're throwing packets at it and suddenly it crashes, but you had no idea what state it was in when it crashed. Now you can't reproduce it and your crash is not worth anything, right? So we want to bypass that issue too. And we'll learn how to do this now. And we'll do it by using emulators, of course. So there are some emulators already available. The two biggest ones, I think, are QEMU and Box. QEMU has a lot of like different architectures which it supports, like MIPS, RISC-V, you have PowerPC. I think you can run basically an architecture in it. So it supports a wide array of architectures, but of course it's built to be a good emulator. It's not built to be a good security testing tool. So it's very good in doing like its proper job. It's very much like the hardware, but it's not built for restarting quickly. And the other one, Box, is a very good x86 emulator for like PC emulation. But yeah, it's also not built for resetting quickly. So usually, this is true. Which means that, okay, you can have more fun building your own and like learning how to do it properly, or you can spend time learning some obscure code base which you don't really want to know anything about, and you might be able to modify it to your needs. So you choose here, and of course you choose to build your own. Yeah, okay. So say we have implemented all the hardware we need to run a program in software. How is that good? Like, what do we gain from this? So we will be able to trace the execution of the target program perfectly. We will be able to know like the exact state of the program counter at any time during execution. Like you can see the exact path it takes every time, 100% deterministically, and it's like great, right? You can see, you can build a map of every path it takes. Since we build the CPU ourselves, we can have like perfect insight to any register at any point during execution, and the same is true for the memory if we build MMU ourselves. And a fourth great thing we gain by implementing this ourselves, of course, is that if we have the memory in a big array, like a big byte array of memory, we can have a corresponding array of permissions, equally big, with each index representing one memory index in the memory array, right? So what this means is that you can get byte-wise memory permissions, which is even better than like malloc and ASN can provide for you. I think malloc has like 16 byte chunks as like the smallest unit. So now you get down to like 1 byte. So it's 16 times better than malloc to do this.
Sorry, Joel.
Yes.
Why is that important? Why do you want to have the permission for memory?
We'll get to that when we look at how things crash. But basically, if some programmer has made a bug and you read somewhere where you shouldn't be able to read, usually if you read like less than 16 bytes outside of where you should be able to read, it won't crash the program. It will work, but you will get the wrong values, right? But now we will see that if you are even 1 byte off, which is very common, like programmers usually do this off by 1 errors all the time. So this is very good. We already went over this. Okay. So now, say you want to build an emulator. Maybe you have found like a target program built for an architecture which there are no supported emulators for, or you just want to learn how to do it, or you want to build a security testing specific emulator. How do you do it? Well, you basically need to read the ISA for the architecture. This is published by the producers, what's the word? The builders of the actual CPU. And they give it like it's a programmer's manual. How does this hardware work, and how do you interact with it from a software perspective? So usually, I think the main consumers of this manual are compiler developers, because they really need to know how to output, like how to generate the code for this certain architecture. But we're on kind of the other side of that. So we want to implement what this thing says that the hardware does. So we kind of switch the mindset around here. So for every instruction that the ISA says that this hardware supports, you need to implement the corresponding functionality yourself. So here is a very crude implementation of an example in a made-up language. So this is kind of a structure which has like 3 fields. We have 32 bits or 32 register, which are 32 bits wide, like MIPS and RISC-V. And we have 1 kilobyte of memory and also corresponding permissions for every memory or every memory index. And say that this ISA only specifies 1 instruction, which is add. Then we only have 1 instruction to implement. And we do it like this. So this is basically everything you need to do, but you need to do it for a lot of stuff. And then you gotta read the program, parse the instruction or the bytes as an instruction, and then execute the corresponding functionality in your emulator. Yeah, okay, so if you've done this, now you'll be able to run the program, right? We don't need any source code, we don't need to compile it, we don't need to put instrumentation in it to fuzz it. Like, you have full control of the environment, and you have full control of the permissions, and you can really easily see what it's doing. Like, you will see how it interacts with memory, and if it's looping a lot, and like what paths it takes, what address spaces in the program it touches. You'll be able to get like a lot of introspection for free, because if you can see the environment the program executes in, you can see like what it interacts with. So it's a really good feature. Yeah, so we get this for free. And another super good thing that this provides us with is the ability to implement coverage guidance super easily. So coverage guidance is when you build your future fuzzing iterations based on knowledge from the previous ones. So say you have a program, you're very interested in some certain parts of this program. For example, say you have an authentication check. You might be super interested if you can get the program to reach like a success branch of the authentication check or get past it or whatever. And this means that you can identify if the program got there very easily because you can see the value of the program counter. Right? This is a register in the CPU which points to exactly where in memory you're executing next. So if you can track this value, you can know exactly where we're going, or not where we're going, but where we are at least. So we can tell, okay, we got past the authentication check. That's very good. Let's continue using this input we used to get past the authentication check, and build upon that in the future. Maybe we can trigger more interesting code paths. Also, this gives us the ability to discard bad inputs, right? So we can pick our inputs which we know are good. This kind of input leads to good paths. Keep building on top of those. Keep mutating them instead of others, making it more like the fuzzer more smart. And this we gain for free, because we have such a good introspection, because we are the environment. If you compare this to like AFL, at least the original AFL, you needed to have source code, you needed to compile it with instrumentation, and you get this specific binary. So you have a lot of prerequisites to even be able to collect this data. Okay. Okay, so that's a lot of good stuff, but there's even better stuff. Say you have like we spoke about, if you have a program that takes a lot of time to start. It takes 30 seconds to start, and it's completely like you need to run this 30 seconds every time, you can't bypass it. Say you bypass it once in like a debugging fashion, like you step through the program until you reach the perfect pre-fuzzing state, and then you save the state of your emulator. This means that you will be able to reset to that exact state later. And if you combine this with fuzzing, you can imagine like after each fuzz case, you just reset your emulator. Instead of spawning a process, doing all the syscalls, running through the startup time, instead of doing all that, you just, boom, like memcopy, it's done. Yeah, and you get very fast resets then. So, yeah, because if you build your emulator in a simple way, like we looked here, like if you do this, like resetting state is like 3 memcopies, or maybe 1 if you hack it together, right? And if you use stock emulators, it's way harder because they have this smart data structure for very good emulation. So they are very similar to how the hardware works with a lot of different memory areas, and it's very intricate. So resetting is not easy. It's way harder. But if you build a dumb emulator that's very quick and easy, you can just memcopy it to reset the state. Like we looked at, we also have like for every byte in memory, we can have 1 permission. We can even have bitwise permission, right? But that would require a lot of masking operations. So then you offer some performance for being able to have this super high granularity of permissions. But usually bytes, I think, is enough. But you can have like byte-wise permissions in this way, which is still like very good. Yes, so now let's talk about crashes. So first, what is a crash? Or we might not even look for crash. We might, like we said, look for the goal of our fuzzing might not be a crash. It might be like reaching a certain state of the program. Like the program counter gets this value or a value in this range. Good. If we're interested in that, we note that input and save it as an interesting input. But usually we look for crashes, because crashes can usually be leveraged to vulnerabilities. So the way you detect a crash if you have built an emulator is that somehow you need to detect that the program is trying to access an address it's not allowed to access. And this can be tricky. So when you load a executable, it usually comes with certain permissions for certain memory ranges. So you can take those into account. You can also do a kind of a hacky way, like saying that the program should never be able to read from an address which has not previously been written to. That's one way to do it, right? So if you're never able to read from an address you have not written to, you prevent use of uninitialized data. And in that way, you can even detect like usages of uninitialized data, right? Which you usually cannot. So here, that's another like specific thing that you cannot achieve without this kind of control. Yeah, so that's the main things we're looking for is like reaching interesting paths in the program and causing crashes. Now, say you found one of these interesting inputs, which led you to note it. Now you need to be able to reproduce it to like figure out, okay, is this a vulnerability? Can I use this to do something else interesting? And for this, you need to be able to reproduce the state which you found it in. And like we said, like this is, you get this for free because you control the state like totally and fully. There's nothing other, there's nothing else outside your emulator. There's no RNG, there's no race conditions. There is like, everything is 100% reproducible. So that's a great thing. Yes.
How do you usually go about finding the interesting spots? Because you talked about some programs are even obfuscated and so on.
Yeah.
So like even getting to that point where you know what path you want to trigger, how does that happen?
You need to reverse engineer the program and find it. So that could be super hard.
Yeah. So you usually build like tooling within your emulator to be able to like step through and so on.
Yeah. Yes. Like debugging and running, you should be able to do. Because you need to, like, before you start fuzzing, you need to single step until you reach the perfect state, or set breakpoints at least. But yeah, you need some reverse engineering for sure to determine this, like the interesting addresses and ranges and such, for sure. So it kind of goes hand in hand with reverse engineering the target. It could also be a great help for reverse engineering, being able to just debug it, right? So dynamically step through it. So I think now we can look at a program I built a long time ago. I think we're good on time, right, Magnus? Or, yeah.
Go ahead.
So this is a, this is a RISC-V emulator. So RISC-V is a quite obscure instruction set, but it's great because it's extensible. So you can build a super small instruction set and then build on top of that. And you can build a compiler which compiles things to this extremely small instruction set, making it super easy to emulate compared to anything else. So the smallest instruction set, I think, is like 42 instructions. So that's like nothing. If you compare it to x86, I think x86 is like 1,500 instructions or something. So that's hard to emulate. So this is like a built-in fuzzer / emulator in one. So first we might want to look at the target program we will run here. Target source risk. No, oh yeah. So this is a small target which has been compiled to RISC-V instructions. As you see, this line here dereferences a null pointer, which causes a segfault. And we only reach it if a buffer we copied from the second argv array is AOEU here. So basically, if we do this, it crashes, right? But if we do this, it returns 0. So let's run this big command here. So this is the name of the fuzzer itself. This is a directory with some inputs. We can look at it actually. So this is very close to the input that makes it crash. So it's kind of a sheet. It's kind of easy for this fuzzer. Using these inputs. Here is the one that's a bit more farther away from the actual crash triggering input. Oh, sorry. Oh, that's the binary. Yeah, well, basically, you have a set of inputs that are not really the crash triggering string, but it's close to it. So it's like you sampled some valid data, and now you want to mutate it to hopefully get the string that makes the program crash, and yeah, hopefully crash it. So to demonstrate the actual running program, we do this here. And you see that we specify the target binary here. It's called target 6. And we provide it with 4 A's as the first argument. This is the architecture, RISC-V 64-bit integer instruction set. And we say use 1 core for fuzzing. So if we run this, it will spew out a lot of information. So the thing it did now is that it took the ELF binary, it parsed it, it found like the loadable segments of it, lifted it into the memory space of the emulator, noted the permissions, and set the corresponding permissions to the permission array we discussed earlier. It also parsed all the files in the corpus, and it built a stack for us to execute this process in, or to emulate execution of this process on. So here you can see that argument 0 was written to guest address hex 200,000, and the second argument was written here, and we built initial stack here, and this is all in guest memory, right? This is in the big uint8 array. It's like it's nothing else than bytes. So now I have a cheat sheet somewhere. Here. So I have reversed engineered this program to know exactly where in memory these things get copied and where we want to take our snapshot in, like exact locations. And this I spent some time to like read the actual instructions to see what's going on. But you just have to take my word for These are the actual addresses. This is the size of the buffer we're interested in. So let's just enter that into the program. So we say break at 10218. I think I did some S break maybe. Yeah, here we can see breakpoints. So we can run continue. And now it says hit breakpoint 0. So this is kind of like a debugger. So now we can inspect the register state. And we see that the program counter is pointing to this value here. So as you can see, like we have full control here of the CPU. Like we can see anything here. Now, I have previously noted that this address is where the buffer gets copied to. Like the argument buffer gets copied there. And we know that we are interested in 4 bytes. So we note that with this command here. This is, this is just how I made it work. And we do length 4. And then you can do options, and it tells you the required steps before you start fuzz. And it says you have set the target buffer, you have set the length, but you have not taken a snapshot. So now we need to take a snapshot, and you do that like this. Now I think everything is set. So we took a snapshot at this address. We noted where in memory to input the mutated inputs, and for the size, or like the size of each input that we should like mutate an input. And now we just do go here, and it should start spewing information. So now it's actually like continuously running the guest program within our emulator over and over and over and over again, taking the inputs from the corpus, mutating them, and shooting them into this buffer at this address we specified. Maybe it's hard to see. I don't know, but if I make it bigger, it gets very corrupted. But as you can see, if we do this, like it executes quite a lot of guest instructions every second, almost 3 million, right? 1, 2, 3, yeah. And it resets the emulator at 1,200 times a second. So that's the like it resets. It does the mem copy of the state this many times. Graceful exits are the number of times the program ran without crashing, and the times it crashes by a read seg fault. The null pointer dereference is a read seg fault. And since I did not implement like any, what do you say? It will never finish. It will just continue like doing this forever. So we need to terminate it now. But so if this was a harder problem, it might have taken a long time to do this. So then you could go into progress, crashes here. Oh yeah, and it noted every crash here. So we could just take one of them. Do this. And we can see, where did it go? Oh yeah, here. So the first 4 bytes here are AOEU, and we got a Q as a bonus here. But the thing that caused it to crash is these 4, right? So it took the buffer and it kind of mutated it, and it found a crash, and it noted the input, right? And That's exactly how it would work with bigger inputs as well. Like this could be entire files. It could be like you could have a storage of pcaps and send them on to some very intricate, like a base station or whatever. And it would work in exactly the same way. But yeah, this is quite a dumb fuzzer or a dumb emulator. If you want to, I could show you like the basic way it decodes an instruction and interprets it and chooses what to do with it. I don't know, I think we're in 40 minutes.
I don't know. Is this available somehow?
Yeah.
The source code?
Yes.
Up to you. 5 more minutes?
We can do 5 more minutes. So we go to source here. So basically, we go to emulator, RISC-V here. So this is where all the stuff is. That here's a good one. So here is, let's take add or something instead. Here's like here's an add instruction. So what the emulator does, it basically it gets an instruction. It interprets the different parts of the instruction as arguments, and it just changes state based upon them. So this is just according to the specification. And if you just do this in RISC-V, you need to do this for like 40 instructions, and then you can run programs totally under your control. So that's great. And a great thing is that even if you were to have source, if you were to want to fuzz like an open source program, and you have this emulator, you can just compile the open source program to RISC-V, and then you can run them in this emulator too. So that's yeah. You need a cross compiler, but that's not super hard to set up.
It's a program you fuzzed just now needed to compile to RISC-V.
Yeah, you need to compile it.
But like you said, emulator fuzzing, it's good for open source.
Yeah.
But if I just give you an executable, can you fuzz it?
If it's RISC-V?
No.
Depends on if I have an emulator which supports the architecture.
Okay.
If it's like a PowerPC binary built to execute on PowerPC hardware, I need to have an emulator which implements the PowerPC instruction set. Yeah, so this is a very small instruction set. It's like 40 instructions, and nothing is built for this. So it's pretty useless. So but yeah, okay, great. Yeah, that's it.
A question.
Yes.
You can run AFL with QE, I don't know.
Yeah, they have a chemo mode. Yes.
How have you, if you compare, have you tried it?
Yeah,
Compare it
it's
to-
super slow.
Okay.
Yeah, it's super slow. But yeah, it works. You can do it. Yep.
You said some programming languages are harder to reverse engineer. What types of languages?
C++.
Yeah.
VTables. Yeah. And Rust is hard too, I think. But yeah. And also you can, like, if you strip your binaries and like you can obfuscate them, everything gets harder, right? So, yep.
What do you do about syscalls?
Sorry?
Syscalls?
Oh, how to handle them. So if you write an emulator which is supposed to run user space programs, you need to handle syscalls. If you write an emulator which is meant to run kernels, you don't need to care about syscalls. So build an emulator to run kernels. But yeah, in this one, okay, let's look at it actually. I have a function here somewhere. where is this function? I wrote this code a long time ago. Syscall. Yeah, so this emulator only supports a very small number of syscalls. It supports close, write, and 80. I think 80 is fstat. Yeah, fstat. So if you run fstat in the guest program, it will give you a predefined file statistics that's not related to the actual file you wanted to know anything about. But yeah, you could do it that, like, if you run the emulator on a Linux system and your target is a Linux binary, you could just offload the syscalls to your actual host system as well. So, but yeah, that's pretty, that's hacky. Yeah.
But then it's no longer deterministic, right?
No, exactly. Yeah. So you should build a kernel emulator.
How do you go about testing the correctness of your?
That's super hard. I have a script for it. Yeah.
So for this, maybe like risk 5, simplest version might be one thing, but if it's a bigger.
Yeah, but this is a pain in the ass to find the bugs in as well, because like the only thing you have to go on is the specification, and if you made a bug, like, it will kind of look like it works, but you have to like compare it to the specification. So what I did building this one is I have a script that this is better to speak about. It's
Could you, for instance, run in the same application in Qemo and
exactly.
compare the memory?
So I have a script that does that. It starts QEMU with GDB, and it steps through the two emulators at the same time, comparing the register state. And if they differ, it says, okay, you made an issue here, or you made an error here. So that's found a lot of bugs in this emulator. Yeah, a good question. Yeah, that's super hard to know. Like, you basically need to have a proper emulator in order to know that your emulator works, right? So
Have you found any keyboard bugs?
yeah, many. Yeah.
Even really small systems now have perhaps more than one core or more
Yeah.
processor. Are you screwed then, or?
Basically, you have to handle that somehow, right?
Yeah.
Like when the context switch occurs, you get some interrupts. You get like you get the indication that, okay, you need to handle this somehow now. So, but that's hard. You need to handle it. So it's easier if you have like one core only you care about. If you build a kernel emulator, you can run like single-threaded Linux, and you don't need to care about that. Yeah, that's my current project. Like, next one, it's a kernel-based one. More questions? All right.
I have one.
Yeah, go on.
Have you considered building like something for like more bare metal, like for microcontrollers, like RISC-V, like for example, like fast firmware of, I don't know.
Yeah.
Hardware. Like there are a lot of RISC-V chips in modern hardware.
Yeah, like IP stuff.
Yeah.
No, I haven't.
Whatever, SSDs, whatever.
Yeah. No, I haven't thought about that. It's a good idea, though. I mostly think about Linux stuff. Right? So. All right.
Let's,
Yeah.
thank